All right, let's get into it. Today, we're going to break down collision theory. You know, the stuff that explains what really makes chemical reactions either zoom or crawl.
Okay, so check this out. This is a super common exam question, right? And here's the answer pretty much everyone writes. Increasing temperature increases collisions, so the reaction goes faster. And guess what? 2 out of 6 marks. Ouch. So why so low? Well, honestly, it's just too vague. The examiner's thinking, okay, how? Why do those collisions matter more? They want the details. And trust me, by the time we're done here, you'll know exactly how to nail that full 6-mark answer. We're gonna fix this right now.
So to unlock those full marks, you have to start with the single most important idea in all of collision theory. And it's this: not all collisions actually lead to a chemical reaction. That's the key right there.
So, look at this first one. The particles kind of bump into each other and poof, nothing. They just bounce right off. The problem? Not enough energy. Way too weak.
All right, how about this one? These guys definitely have more energy. You can see it. But nope, they just glance off each other. The angle was all wrong. Still no reaction.
But these particles, now we're talking. Bam, a head-on collision. They had plenty of energy and they hit at the perfect orientation. And that is when the magic happens. We get a reaction.
So let's put that all together. For a collision to actually be successful, to cause a real reaction, 2 things absolutely have to happen. First, the particles need to smash together with enough energy. We call that minimum energy the activation energy. And second, they have to hit each other in just the right way, the correct orientation. Okay, so let's really think about this. Why does energy even matter? Well, think about what's happening. To make new stuff, you have to break the old stuff apart first, right? Breaking the bonds and the reactants, that takes energy. It's like trying to snap a twig. If you don't push hard enough, nothing happens. Same here. If the collision is too weak, less than that activation energy, the bonds don't break and the particles just bounce away. No reaction. And what about the orientation? Why is that so important? I love this analogy. It's like a key in a lock. You can have the right key, but if you try to stick it in sideways or upside down, it's just not going to work. It has to be aligned perfectly. Molecules are the same way. The specific reactive parts of the particles have to line up and meet for anything to happen. Okay, so what does this all boil down to? It means that whenever we look at something that affects reaction speed, like temperature, concentration, or a catalyst, we need to ask ourselves 2 critical questions. Question 1, does this thing make the particles collide more often? That's what we call collision frequency. And question 2, does it increase the percentage of those collisions that are actually powerful enough to work? That's about collision energy. Let's use this framework to look at a real example. All right, first up, temperature. Let's break down exactly what happens step by step when we crank up the heat. So step 1 is pretty straightforward. When you add heat, you're basically pumping the particles full of kinetic energy. And what does more energy do? It makes them zoom around like crazy. They move a lot faster, which naturally means they're going to bump into each other way more often. And that's our first effect, an increase in the collision frequency. Okay, but here it comes. This is the crucial detail, the part that separates the 2-mark answers from the 6-mark answers. This is what most students forget to mention. See, it's not just that they collide more often. Because they're moving so much faster, the collisions themselves are way more powerful. They hit with a lot more force. So at that higher temperature, a much bigger percentage of the particles now have enough energy to get over that activation energy hump. And what does that mean? It means a much higher proportion of collisions are now successful collisions. So you see the double whammy? Temperature increases both the frequency of collisions and the energy of those collisions. That's why even a small temperature change, like 10 degrees, can literally double or even triple the reaction speed. This is the complete picture. This is the reasoning that gets you all the marks.
Okay, so that's temperature. Now let's switch gears and compare that to what happens when we increase the concentration.
With concentration, what are we doing? We're just cramming more particles into the same amount of space. It's like a more crowded room. So yeah, particles are going to bump into each other more often, for sure. The collision frequency goes up. But, and this is key, did we add any heat? Nope, the temperature is the same. So the particles aren't moving any faster. The energy of each individual collision hasn't changed at all.
And that right there is the crucial difference that examiners are looking for. You can't just say more collisions for everything. You have to be specific. You have to explain which part of the collision is changing, the frequency or the energy, and why. Okay, time for a little challenge to see if you've got this. Picture this scenario. Someone adds a catalyst to a reaction. The rate shoots up, but the temperature doesn't change at all. So using what we've just learned about collision theory, how would you explain exactly how that catalyst is working? Go ahead, take a second and think about it. What's really changing here? All right, you ready? Let's walk through it. The very first thing a catalyst does, its main job, is to provide a whole new, easier pathway for the reaction to happen. And that new pathway has a lower activation energy. Now remember, we didn't change the temperature, so the particles are all still moving at the same speed. They have the same energy they started with. But here's the magic. Because the goalpost has moved, that activation energy is now lower. Way more of those everyday normal collisions suddenly have enough energy to be successful. It's not that the collisions got stronger, it's that the requirement to succeed got easier. So let's sum it up. The catalyst doesn't change how often the particles collide, and it doesn't change how much energy each particle has. All it does is lower the bar for success, which dramatically increases the proportion of successful collisions. See that pattern? We identified what changed, explained the how, and stated the result. You can use that exact same logic for any factor they throw at you. And just like that, you are totally ready for any exam question on this topic, because you've moved past just saying more collisions. Now you know the real story. If they ask about temperature, you'll talk about kinetic energy. If they ask about concentration, you'll talk about particle density. And if they ask about a catalyst, you'll talk about lowering that activation energy. You've got this. The big takeaway here is that you now understand why these factors change the rate, not just the fact that they do. And that right there is the difference between just passing and true mastery. Hey, if this helped you out, please do a huge favor. Like this video, share it with your classmates, and of course, subscribe and turn on those notifications so you don't miss the next one. Thanks for sticking with me.